Good morning, everyone. Just making sure my camera is correct now that I've changed my camera angle, and I'm like halfway between the laptop and things. Michael's wondering if anyone else is feeling really busy right now. I'm sure everyone is. We're getting down to the business end of all of the subjects that you're doing at the moment, so I'm assuming most everyone has a second assignment for every subject that they're in right now. There's usually going to be something people are doing to wrap up what they're doing. Dylan, fresh cut, and Sam, yes. So I've refreshed the sides of my head, and I'm quite happy with that, as usual. But I'm keeping my fringe because I love the fringe, so it's getting long, which is fun. If anyone watches The Expanse, my haircut is based on Miller in The Expanse when around the time where... Oh, actually, no, I'm not going to say anything about when it is, just in case people do want to watch The Expanse. I'm not going to tell you what happens in the story. But yeah, sometime around, not the very beginning, Miller, but somewhere around the middle, he ends up with a haircut a bit like this, and I've been modelling mine on his for a little while. If you haven't watched The Expanse, you can check it out. It's pretty cool. It's a very, very interesting TV series. What was I going to say? Did anyone check how many people were here? Because I wasn't even here at like about 10 to 9, because we had a discussion last week about there being more people before the beginning of the lecture on the afternoon lectures than there were in the morning lectures. I'm going to get the feeling that there were less people waiting before the start of the lecture in the morning than there were in the afternoon, especially with weather like this. I don't know if everyone's in Sydney. I assume not everyone is in Sydney, Australia, but Sydney, Australia is very, very dreary at the moment. It's been raining. It's very wet and cold and windy, so I think it's actually a pretty good time for not bothering to go outside and just hanging around indoors and doing things instead. Someone said it was 13, which was significantly less. Okay, Jed saying 43 was, I assume that was afternoon. We don't usually have 43 people waiting at one time. Duke is wondering about the difference between version 1.41 and version 1.1 of the assignment. I'm pretty sure... I can't remember exactly which thing it was. I'm just racking my brain off the top of my head. There's one little thing that's changed in that time, but I think that if you have already written code for what was in 1.1, the changes are more likely to be that the spec was clarified to match what people had already done. Because we had some things that auto tests was implying was happening in a certain direction, and it was different from what the spec was saying. So what we did was change the spec rather than the auto tests. Because if we change the auto tests after the assignment's released, if we change the auto tests or the reference implementation, we have to be very clear and let you know that, because that means you have to change your implementation. But what we do most of the time is we change the spec so that anyone who starts later ends up doing the same thing that people who started earlier did, if you get what I mean. So if people do something based on the reference implementation and the auto tests, then we change the spec to become closer to what those people were doing. Rather than if we've made a mistake in the consistency between the reference and the spec. We usually don't want to make people go back and have to change what they did. But what we'll do is we'll make it so that anyone who starts later and gets to that point will get the new information instead. If you get my drift. I would still look at the changelog and check the differences between the 1.1 that you had and the 1.4, and see if there's anything that you think might be causing issues that are different between yours and the current version. But I would say stick to the idea that you're trying to complete the assignment to the auto test and the reference implementation, because they're less likely to change unless there's an actual bug. So there's an actual kind of completely incorrect thing going on there. They're less likely to change than the than the spec. The spec will often change to fit those things instead. Xiao Yu saying, still confused how the tests work. So there's the test realm file, and in the test realm file, we ask you to write tests. So these are the same as like the auto tests that we'd been running on your code. We'll ask you to actually write some code that's going to test someone's realm.c in a sense, and we've actually created a realm.c that sometimes works and sometimes doesn't. Sometimes works and sometimes doesn't. So with our realm.c that we're testing with your code, we're asking you to see whether you can find out what the errors are in our realm.c. So the auto tests with your test realm.c are not actually run with your realm.c. So our auto tests that test your testing, I know it's it's layering things on top of each other, but our thing that tests your testing gives you a program that we've written, which is basically the reference solution with us chopping bits out of it, or us making it not work under certain circumstances, and we're seeing whether your testing can find those circumstances or not. So whether you can pass those auto tests or not is a matter of saying, can you find out whether our program is fully working or not? And it's not necessarily like you can actually get very, very good marks in that without passing all of the auto tests, because even if you're not catching exactly the things that we're doing, you can still get marks for writing good tests that are finding some information out about our not perfect implementation that we're testing on you. So hopefully that gives you some information about what we're doing with the testing. Is basically we have given you the opportunity to write tests the same way we write auto tests, and then we've given you the idea of an imperfect assignment that you're testing. And then you can see whether your tests can find out everything that is and isn't working in the imperfect assignment that we give you. So it's leading you towards the idea that eventually, when you're writing code, there's no auto tests, right? There's nothing that is given to you that already knows the answers. You'll have to figure out whether you think that the program has the answers or not. So that's why we give you another version of the program that's not 100% working, and you have to see whether you can get that, whether you can find out what that's working or not. So that's why you see the auto tests for the testing part of it will say, what does it say? Does meet the specification or does not meet the specification, and you get a green line that says does not meet the specification. And what that means is you've successfully found out one of the points of our version of the assignment that doesn't meet the specification. So you've tested well enough to be able to find out those issues. So little things like that. I think that's pretty handy, because this is a skill that's going to come in very, very handy, knowing how to pick apart something and find out what's working and what isn't working in it. So you have to do that with your own code a lot. We do it manually a lot. Having it done in this automatic way where you write a file to test your file is a pretty common thing. We call it unit testing. Michael's asking, just to make sure, our testing code is for testing another piece of code, not our own. Kind of. You can definitely use it to test your own as well, but just to make it easy on you to test whether your tests are working, we've given you some auto tests for them to see whether you can get them going. Duke is asking, if I do 1511 setup again, does my work disappear? I think it does, but I'm not sure. I think if you do 1511 setup again, I think it will refuse to copy over the files if they're currently there. So I think running 1511 setup again will do nothing. Although I think it will update the files that are links. So it'll update the files that... Actually, they may have already been updated automatically. It won't update the realm.c and the test realm.c. But I think you don't even need to run 1511 setup, and the files that are linked to our files will already have changed. So you won't even have to do anything for those. Oh, sorry, Tom's saying, yeah, 1511 castle defense will do nothing. 1511 setup castle defense will do nothing if you've got files there. So it'll only copy files in if it doesn't see that there are files there. So it's like ultra safe. It's made to not copy over any of the things if you've already got them. David, nice haircut. Thank you very much. Okay, some other questions to answer before that. I thought I saw another one up there. Riley's asking, downloaded on Monday, realm.c says version 1.00. I'm pretty sure that's correct, because each of the files actually has a different version. So the realm.c hasn't changed very much at all, but some of the other files may have changed. If you want to check whether you have the latest version, you can start a new directory, and then run 1511 setup there and have a quick look at the version numbers in that directory and see if they're the same. Okay, we've got a whole lot of other questions that are just about the assignment. I'm going to leave them for the moment because I need to actually get into lecture content today. But if you need to, talk to your tutors, talk to a help session, ask on the forums. Your questions will definitely be answered, but there'll be a time and a place where they'll be answered. So I had a little bit of a talk about the assignment, but I don't want to use too much of the lecture time just talking about the assignment. We have actual content that we should be going through. Okay. Oh yeah, and Tom's answering some of those questions there, so he might be able to answer those questions while I'm talking about other things. All right, on to the lecture. So, what did we learn last week? I'm just gonna... Which way is the arm? Is that right? Yeah, I think that's right. I gotta get the arm to line up. Yeah, okay. So, last week, we did linked lists. We spent the whole week just on linked lists. So what we managed to build last week, I think, is the biggest program that we've built in the lectures, because there isn't really that much time to program in the lectures when you consider that we do 2 hours at a time of lecturing. And what I built over the 2.5 lectures that we were working on linked lists is nearly enough in terms of how much it did to pass the second assignment. I mean, it's not, because it doesn't do castle defense, but it does a lot of the same operations and a lot of the same thinking, a lot of the same logic that that castle defense requires for you to pass the second assignment. It's done that way on purpose to show you all of the types of operations that we would need to do to be able to work with linked lists. So we've got the creation of the linked list by memory allocating nodes, knowing how the structs work, knowing how to move pointers around to be able to manipulate the linked list and change the way it's laid out. And we've got insertion and removal of nodes specifically that we worked on. And we also looked at cleaning up memory. So we looked at how we could loop through a linked list and clean up each node as we're going along. Things can get more complicated. Obviously, if you want to get deeper into the second assignment, things get much more complicated than that. So the algorithm I showed you that goes through and cleans a linked list was always kind of moving 2 pointers to make sure that you have access to the list with one and the other one would remove what you've just gone past. So that kind of cleaning up worked pretty well. In the assignment, you may have more stuff than that, because some of your linked list nodes might be aiming at another linked list of enemies. I think we missed out on the opportunity to rename enemies to foxes, because we wrote enemies. So we wrote the assignment, and then we saw the whole Frankie thing, and we were like, oh, this is hilarious, we're putting Frankie in the assignment. Yeah, so all of the work that we did over the last 2 weeks learning about linked lists and learning about how to use them, you can use any of that work in your assignment. Obviously, I've written it in such a way that it's useful, but not an exact copy, because what I want you to do with the assignment is I want you to be able to see what I've written, have enough understanding about what I've written to be able to modify it to use for the assignment. So it's really set up in that way to show you how these techniques work and then give you a chance to practice using them. And practice doesn't involve copy pasting, because if you just copy paste stuff, you're not really practicing it, which is why the assignment questions are subtly different from the battle royale that we've created, but they're different enough that we want that we give you a chance to learn how to change them without necessarily throwing you in the deep end altogether. So if you're having any trouble with the assignment, I suggest going back through the lectures again. You may want to watch the videos in a situation where you can pause things and you can copy down the code that I'm using, or you've actually just downloaded the code that I'm using and you have a close look at it and you try to figure out exactly what each bit of code does. And when you've got a good idea what each bit of code does, you'll have an idea about how it's going to change if you change bits of it. And you can also go in and do the same things that we do when we're debugging, where you can change parts of the code and see how the behavior of the code changes, and then by doing that you'll learn a lot about how it works. There are some questions there, but I think Tom is answering all the questions there. So I think there's just a lot of assignment questions there that Tom's answering, so that's cool. All right. So that's last week. Today we're starting to look at, although I shouldn't say starting to look at, because I've been showing you these things for a while, and just sort of sneakily dropping hints about what these things are. But today we're going to look at the most interesting concept called an abstract data type. An abstract data type continues on from what we were doing of multi-file projects. So we'll do a recap of multi-file projects just to remind you of what they are. Or anyone who's working on the assignment already is getting a decent idea about how multi-file projects work, because the assignment is set up to have a multi-file project in it. And also the assignment is set up for one of these things, which is an abstract data type. So we're going to talk about multi-file projects, a little bit about what typedef is. What typedef is not really that hard to grasp, because it's just something that says these two things are now the same thing. But we're going to talk a little bit more about why typedef is, not what typedef is. So there's a reason why we might want to make a pointer to a struct not even look like a pointer to a struct. We might want to make it look like an abstract object. So there's some really cool stuff going on here. So we're going to talk about the idea of an interface, being that we can use part of a program without knowing what it is. We've been given an interface to something, which is to tell us, here are some functions you can use with this particular object. This particular object has a name. Underneath this is a struct that defines what it is, but you don't even know what that is. You just assume that it is something and you can use it. Or on the other way, on the other side of the interface, you can create something that gives someone different kinds of functionality, but you don't know how they're going to use it. All you can say is, like, here are some functions. You can use those functions to make stuff happen. So as we get deeper into this, you'll see the beauty of being able to sort of guarantee that there's two bits of code and there's a line in between them. And in this line in between them, there's specific functions that go back and forth. And so long as both sides agree on what those specific functions are, you can go back and forth and use things, and you can change a lot of the code on one side without affecting the code on the other. So there's some really, really cool stuff going on there with abstract data types. It's actually one of the ways that we can often make it really easy to work in a team, if we can sort of separate everyone's code through this interface of what people should or shouldn't be able to do. Okay, recap of what we were doing previously, linked lists. Yeah, so we've seen a fair bit of this. If you've been doing the assignment, you have no choice but to have seen a fair bit of this. So we've been covering this in lectures. So a linked list is made up of each of these nodes. Node is not actually a keyword. Node is just a human word to say this is what a piece of a linked list is. Each of these is defined by a struct. So the key elements of the struct is that it has a next pointer that points to another struct of the same kind as itself, and then it has some information that it carries. So each linked list node has some information, but more importantly, I guess, even than the information, is it has a way to link to another node. And the way that we will have a linked list is always we'll have a pointer to the first node. It's often called the head pointer, but sometimes it'll just be named. That pointer will be named for what the whole list is. I'm thinking about the enemies pointer inside each location. So instead of it being called head, because head would imply the start of a list, it's called enemies to imply that this is access to a whole list of enemies. So each of these pointers will point to another linked list node until the final one will point at null. And pointing at null is its way of basically letting us know that if we're going to loop through this list, that there are no more on the end here. A recap of what we did last week is we looked at insertion into linked lists. So I think I've got the insertion code here, but not the removal code. But oh no, wait up. We did insertion first and then removal later. So I should have code here. Not code, but revision here for the insertion as well as the removal. So, in order to insert into a linked list, I'm actually going to jump straight to the diagrams because the diagrams will give us a little bit more information. So, to insert into a linked list, so let's say I had this linked list already and I had 2 nodes in it. First thing I do is create a new node. To create a new node, I will do a memory allocation. So very often I will have something which is just a function that just creates the object. It doesn't do anything more than that, just creates it. And this is, underneath this isn't just learning about how to do linked lists, it's also learning about how to separate things into functions. So a whole lot of the Battle Royale thing shows you how many functions we might have in order to do something in a program. And we get to the point where each function serves only one purpose, so it's only got one small thing it does. And then if we want a function to do, 3 things, we might actually separate that into 3 functions and then have another function that calls all 3 of them one at a time and says, okay, I do this chain of events. So hopefully that also, the Battle Royale thing sneakily taught you a little bit also about how to separate things into functions, because I know that was a big question when we first talked about it. And it's hard to teach it without sort of larger examples like this. Okay, so we have a function that creates a new node, allocates memory for the new node so that it lasts longer than the function itself. And I've got some random values in here, so just some numbers. In order to insert this node into the linked list, I need to be able to move these pointers around so that this sequence joins up in the way that a linked list should. Every next pointer is pointing at another node in the list. The final one's pointing at null, and they all chain together. So the first thing we do is we connect the new node to the node that's after it in the list, and we do that by copying the next node of this first node. So the next pointer of the first node gets copied in here so that they're both aimed at the same thing. Then we change the first node's next pointer to aim at the node that we're inserting, and then we can see visually that this is all connected up. The thing that will catch people out the most is how to move pointers. So the thing to remember is, if you change the value of a pointer, so if you treat a pointer like it's a number, and you just say, copy this number into this number, then you will move this pointer to aim at the same thing that this pointer aims at. Likewise, if I say I have a pointer somewhere to access this new node, and I will always have a pointer to something I've memory allocated, because malloc gives me back the address. So the address of something is the same as the pointer to something. So the address is the value that's stored in the pointer, in the same way that a number is the value that's stored inside an integer variable. So they will, I shouldn't say they're the same, but they're interchangeable in terms of the way we use them. So if I have the number address of this node somewhere, I can set this pointer to that address. And that's as simple as saying first node next equals new node's location. So sometimes this is going to be the AND of something, or sometimes if I already have a pointer to something, it means I just copy the pointer to that node. And once we learn how to change pointers so that they aim at different things, once we learn a few basic techniques to be able to do that, linked lists become reasonably easy because we can just follow this logic to make them work. What do we... Oh, right. Tom's just having breakfast, I think, and everyone's asking him assignment questions. Yuji's tired. I can imagine, yeah, at the moment. I'm also very tired. I only woke up like half an hour before the lecture started, so I was just like, rushed through my breakfast and just like, all right, get ready. We've got new things to learn. I should say also, because I know it's definitely happening. There's only 88 people, 89 people in here at the moment. You can go back and watch the lectures later. This is like just basic educational theory. If you're really tired and you're not focusing on things, it's less likely that you're going to be able to understand what's going on. You could, if you wanted to, go back, have a nap, wake up in the mid-afternoon, well, depending on how long your nap is going for, and watch this later. I don't think, especially when we're talking about online learning, I'm not in a situation where I think I need to force anyone to take part in the lecture at a specific time. So Vincent says you get up at 6:50. Are you in China? Is this a 7 a.m. start for you? Because like I think that's some serious commitment. I would have a lot of trouble at doing a 7 a.m. start for a lecture. I apologize to you. All of the organization for this term was actually done late last year. So we didn't even know that the coronavirus existed late last year when we were doing the timetabling. If we'd known that we were definitely going to have people coming online from different countries, then we would have changed the timing. Because we know that like our major location for our international students is China, and so next term we've actually shifted all of our lectures to the earliest possible start is 11 a.m. so that anyone in China, the earliest possible will be a 9 a.m. start for people there. I apologize, doesn't help you now at 7:30 in the morning. Thank you for coming along though, because that's a big deal that you're willing to commit to come that early. But there will always be recorded videos, and I suggest anyway, if you get to the point where things aren't working that well for you, to go back and rewatch the videos anyway. Riley's saying getting up at 5 a.m. to make it to uni at 8. That's rough. I mean, I hope that a lot of people are getting something out of the fact that we're going online. So for a lot of people it's a disadvantage, I understand that. But for a lot of people the lack of commute and coming online is something that makes our courses more accessible than they were otherwise. Yuji's asking if I teach COMP1521. I do not. At the moment, I only teach COMP1511. But I have been teaching COMP1511 non-stop since the start of 2019. So it's enough work as it is to deliver the same course 3 times a year. Morning, Dean. Yeah, Dylan's saying the lack of traveling makes it so much easier. Yeah, I do understand at the moment that our a lot of what we're doing with our courses at the moment is really, really important for accessibility. And accessibility, you know, people often think of accessibility as like making things better for people with disabilities or something like that. And so they think of it as something that doesn't apply to them. Able-bodied people, we tend to think of accessibility as something that doesn't apply to us. But when we think about accessibility in a realistic sense, it means that these streams and recordings are better for anyone who would have to commute otherwise. They're better for anyone who has temporary issues. Like, even if you have internet connectivity issues or your computer isn't working that well, all this stuff is recorded so you can see it later. So it's really interesting when we work on things, because I do a lot of thinking about how to present stuff in the most accessible way possible, and what it does is it ends up benefiting way more people than we think it does. So if we just do something really, really simple, like the simplest thing people often think of is like putting ramps in so that people with wheelchairs can access a space. We don't realize how useful that is for everyone. Just sometimes it's really useful because sometimes someone happens to have a suitcase with them and they're fully able-bodied and they would think that they never needed a ramp to get in somewhere, but that one day where they've got a suitcase, suddenly everything's nicer and easier for them. And so we get this kind of benefit where when we make things that are more accessible, we don't realize the hidden benefit of doing that. Anyway, random other stuff to talk about. So yeah, I'm glad that the online thing is working for a lot of people. Alex saying things aren't necessarily good for people with dyslexia. Yeah, I apologize. I'm not even sure. Maybe I need to do a bit of research on how to make things better for people with dyslexia, because I've got a lot of words in my slides. I do that so that people who don't necessarily hear me that well, so anyone who's hearing impaired or anyone whose native language isn't English, can actually read the slides instead of listening to me and get a lot of information. But I've not done much research into how to make things better for people with dyslexia. So Alec, I will look into that and see what we can do. Okay. Okay, let's continue. So we've got removal from linked lists, a little bit of an aside there. So removal from linked lists involve bypassing the node that's hey Alec, if you know more about it, send me an email. I think this would definitely be worth talking about, and I reckon like any changes that you think are going to help, let me know, because I'm totally open to trying to make the course more accessible to everyone. And I'm sure that whatever changes I make for your friend that has dyslexia is actually going to help everyone, because it's probably going to clarify a lot of the stuff that I say and do. Anyway, we'll do that. We'll do that later, outside of the lecture. Okay, so removal from linked lists involve skipping the node that you want to remove to make sure that the rest of the list is still consistent and together, and then making sure that after we've taken that node out of the list, we can still use the memory that node was using by giving that memory back to the computer. So it's going to look a little bit like this. Oh, I should have numbered these the same as the list I just inserted into, but I think I wrote these slides completely separate from each other. So yeah. Anyway, we've got 3 nodes here, and just to make it easy on us, we're going to remove the one in the middle. We do need to do different things when we're removing the first node or the last node, but we've got deeper examples for that that I've shown inside while we were writing the Battle Royale. So let's say we're trying to remove the second node. What we will do is we will make sure that the linked list is complete without the second node, which means we need the first node's next pointer to skip the second node. And we know which node's after the second node because it's the next of the second node gives us access to this node. So what first node is going to do is it's going to say, I am going to copy this pointer into here. So I'm going to replace my next with the second node's next, and that's going to skip over, and it's going to be doing this. So first node's next to bypass the node we're removing, so this next has to be equal to this one in order to skip the second node. While we do this, we're going to make sure that we maintain some way of accessing the second node. Usually we'll have a pointer to this one, whether we name it like pointer to the node that we're removing. We probably don't want a variable name that long. I usually call it something like rem node or something. So I will keep a pointer to this one, because if we bypass this second node without maintaining access to this second node here, we're not going to be able to free this memory, and we don't want to leave this thing hanging around, because after we've removed it from the list, chances are we're not going to use it again, because if it's not in the list, it might not be important to us anymore. So if it is not important to us anymore, we don't want to maintain access to it, we're going to free this memory, which means we needed a pointer aimed at this to free. We free it, it disappears, that memory is then accessible for us to then use for other things in the future. So this section of it, as we can see now, is a complete linked list. It's got a pointer to the first node, each node is chained to another node via the next pointers, the final node has a next pointer aimed at null, fully valid linked list here, and this piece of memory that used to be our second node has been given back to the computer to use for other things. Talking about dyslexia, Comic Sans is one of the best fonts for reading. Wow. That would be really funny. I used to troll artists when I used to teach a combination of programmers and 3D artists in computer games. I used to troll the 3D artists by writing stuff in Comic Sans with rainbow colors and things, just to see what they would think, because they have a proper sensibility of color and font and stuff. And Comic Sans is really famous for being a font that is very I guess aesthetically not pleasing, but if it's easier to read, then maybe that's actually a better thing. Tom's saying sans serif fonts as well. It doesn't have to be Comic Sans. We could use Helvetica instead. Wait, is Helvetica sans serif? I think it is. Anyway, let's move on. Okay, so let's go back over multi-file projects. We now... It's not even trolling. Artists just do that to each other. Yeah. Okay, so we now have a lot more knowledge about multi-file projects than we had before. Previously, when I first showed you multi-file projects, I think everyone would have just been like, oh, okay, you're splitting stuff into files. I have no idea why you're doing this, you know, because that's always what it's like. When I first introduce a topic that hasn't had its full justification yet, it's harder for it to kind of sink in. But I did want to at least show you that these things existed before we drop the assignment on you. But now that you've seen the assignment, you have a decent idea about how multi-file projects work, right? So things are separated into files. They're usually in pairs, not always, right? Because our main file's not usually in a pair. But a lot of the sections of our code are in pairs. There's a header file and a C file. And you'll know they're in a pair because they have the same name. So the same name but different extension. So the extension is the thing after the dot for the file. The header file says this is what the capabilities are of a section of code. I'm going to call it a section of code because it's not, I'm trying to think of a good word for it. You know, it's not an object, but it's a set of capabilities. The C file, the implementation file, is the thing that contains all the code that runs. So the header file is like something that says, okay, here are the things that I can do. You don't need to know how I do them, but these are the things that I can do. And the implementation file, the C file, says, okay, this is how I did everything, but it's really hard to see how it fits together in the C file. You see how it fits together in the H file, and the C file is like drilling down into the nitty-gritty and saying, okay, this is actually the step-by-step of how we do everything. Any other file can include a header in a program that's compiled with the C files to be able to get access to the functions and other declarations and things that that make up this abstract object. I'm going to start using the keywords because sometimes it's going to be an abstract data type that we're using. And now that I've told you that keyword, I'm going to show you how that all goes together. One of the cool things about the header files, and you've got a really good example in your second assignment, you can see how we chain everything together so that it works. One of the cool things about the header file is both sides of the header file, this is exactly what I was talking about earlier, both sides of the header file see the functions that can be used. And they see the object that can be used with those functions. And they see it from its own context. So a main file, for example, that is including a header file says, I have these functions and this object. I'm allowed to run these functions using these objects. I can create these objects because I've got a type definition that says this is now a type that I can use. And then I can pass these objects into these functions, and I expect something to happen. What I expect to happen is what has been told to me in the header file. I do not need to look into the C file to know what's going to happen because the header file has been documented well enough to be able to do that. So, in a team working on a project, we have the H file in the middle. We've created the H file as a team knowing what a component needed to do. And the H file says these are the things you can do with the component. You do not get access to the struct. It's important actually that we don't get access to the struct because it means that we can't make a mistake. So we can't change the data in the struct in a way that breaks the rules of the struct itself. So this way we stop people from breaking the rules of the struct, but we say, yes, you can still sort of access it. And the way you access this is by calling the specific functions that cross over this line. And so what we can do is we can give the C file to one programmer in a group and the main file to another programmer in a group. And so long as they've agreed on the H file and they don't make any changes to the H file unless both of them agree that they should change, you can have two separate people working on the different parts of this. And they will never have a problem so long as they interface to the H file correctly. And so there's this beautiful way that we can separate things entirely. And the person making the main file doesn't have to know how the C file is being made. So long as the C file supports the H file, it's going to work. So it's this beautiful, beautiful way of being able to separate code and guaranteeing that things are going to work for both people. And it gets even more complicated in bigger teams and stuff like that. So it's a pretty cool thing to do. Okay, so I jumped past the recap and started talking about abstract data types. Sorry, when I get excited by concepts, you'll find I'll start talking about it anyway. So remember that when we're using a multi-file project, any file that includes the header is able to use the functions in the header because the C file is actually compiled with it. So the C files are compiled, the header files aren't compiled. They're part of the project because they're included somewhere in the project. And if they're not included in the project, then they're not going to be used, right? Because you can't call a function unless you've seen its declaration. And so this is the same as, and this is why right back at the beginning, well, not the beginning, but earlier on when we were learning functions, we had your main and we said, declare what the function is above the main, just a one-liner declaration, and then implement the function below. So you've got your declaration, which is also called a prototype of the function up the top, and down below we said, okay, now you can write the whole function. And initially people were like, why are we separating that? Why can't we just put the whole function up the top? And now you know why we're separating that. Because the header file only has the declarations, the single line declaration prototype of the function. And what we're doing with the hash include is we're putting all of those up there. And then all of the functions with the body and all of the code in it could be considered the same thing as the C file just being elsewhere, somewhere entirely, that's compiled along with the main file, and the main file has access to it. So what we did was we took that layout of the functions at the top, main, next, and then all of the implementations of the functions below. So we've taken that and we've separated that out into different files. So yeah, you can kind of see how the way we teach things is we see what is the goal we want to get people to, what do we need to teach them in order to reach that goal, how do we work backwards to give them the right information to get there. So like there's a lot of stuff we've been doing where it's like, bear with me, you'll understand why this is later on. And I hope people are now getting to that understanding. And I also hope we're talking about, when I talk about, okay, this is why these functions are like this, people are now saying, yeah, I can use functions. As opposed to, I think, was it week 4? No, it would have been week 3, I think, when I first introduced functions, would have been like, oh, these are really confusing. But now they're probably starting to click. If they're not starting to click, that's okay. you've got a lot of context here. You can actually go back and watch the function lectures now, and they might actually work really well. Hopefully. I mean, it's how I designed the course, so I hope it works like that. So, yeah. If it doesn't, let me know, because it means I need to do more thinking about how I want to do things. Okay. Here's an example of an abstract data type. And I hope that this example resonates quite well with you, because it's your second assignment. So, we've got a realm, and the realm is made up of an H file and a C file. So Castle Defense works like this. Castle Defense is an abstract data type. This is an example of it. So we're not actually really going to ask you to create these things from scratch in COMP1511, but they're really, really useful to know about later, because they're the kind of things that you're definitely going to be using in the future. Oh, there's a lot of chat there. Oh, that's all right. I think Dean's answering a lot of questions there. Tom's answering questions. So I'm going to leave you two to answer those questions that are in the chat. So, realm.h and realm.c are the files that say what a realm is. Note that in realm.h, we only have a couple of hash defines, the things that are going to be needed in the main that might use it. We're going to have typedefs, and we're going to have function declarations. It's commented a lot so that someone who looks at the realm.h can set up something. So you could think of it like this. We set up the H file as a software development team between us to say that we want a certain capability to come out of the realm, and we want to build this interactive game, in a sense. It's not entirely a game, but we want to build this interactive program that uses the realm. And we have two people to work on this. One person is Tom. He's in chat right now. Tom is writing the main file. I'm pretty sure you wrote most of the main file, didn't you, Tom? I think you wrote all of it. I'm not sure. There may have been other people involved, but mostly Tom wrote the main.c with no idea about what you would write for the realm.c. So the two people on the team is Tom and yourself working on a software project together. So he's writing the main.c, and between you, there's an agreement that the realm.h is not going to change. That agreement is kind of strongly dictated by someone like me, because you don't even have access to the file to change it. But you can implement the realm.c, and the beauty of the realm.h and the realm.c is that there's like 750 of you who are all going to implement the realm.c differently. So you're all going to write different code in the realm.c, and they're all magically going to work with Tom's main.c. Now you think about that, that's actually astounding, because there is no way that I would expect 750 people all to be able to write code that would be able to interface with one person's code. But the trick is, because the realm.h is fixed, and it says these are the exact functions that you're going to implement, these are their inputs and outputs, and this is what we expect them to do in the realm.h, you have that interface boundary. So that anything that you implement in realm.c, so you could implement a triple nested while loop for something, I don't know which part of it, and it would need that, maybe something to do with the enemies, triple nested while loop, that's fine. Someone else does it with a double nested while loop that calls a different function. So your architecture is completely different between the two of you. But so long as you meet what we agreed realm.h was going to do, so long as you get to what realm.h said it was going to do, Tom's code, on the other hand, will use your code, and it will be happy with whatever code either of you wrote, so long as the comments and the specification that we decided on in realm.h is met. So it doesn't matter if your realm.c code is different from other students. It's all still going to work, and that's the beauty of having this H file as this crossover point between them. And so what we have is the difference in the H file is really, really human based. It's got heaps of comments. It only has the barest bit of code, whereas the realm.c is very, very much more computer based, where there's heaps of code. It doesn't mean there's no comments. Like, we still need to explain our code in case we want to modify it, in case anyone else wants to read it. But it's completely viable for someone not to read the realm.c if they're developing the main.c. Like, for example, Tommy's not going to read the majority of the realm.cs, but we're still going to trust they're going to work because they work with the realm.h. Likewise, you don't need to read the main.c to be able to develop the realm.c. All you need is realm.h. We could actually give it to you without main.c, and we could say we're just going to use it in some way, and it would still work. So you could never see main.c and you'd still be able to develop realm.h. That's the beauty of the kind of boundary between the two that we're creating. So the main.c is going to include the realm.h so that it can use the functions in realm.h. The test realm.c, interesting thing, is also going to include realm.h, but the test realm.c and the main.c actually are two completely separate projects. They're separate programs as well because each of them have main functions, so each of them are going to be able to use your realm.h in completely different ways. So I shouldn't have said realm.h. They're going to use your realm in completely different ways. So the beauty of this is you've created realm.h and realm.c. So let's just say you had created realm.h. What you've actually, in a sense, created is a way for other people to use this idea of a realm, but you haven't dictated how it should be used. You haven't dictated how the game should run or anything like that, and we could then build a game out of that if we wanted to. We sneakily did this in the first assignment as well. You notice that you could run it in a way that would just add lines, fire the laser and stuff like that. Or if you wanted to, you could run it using Dean's implementation, which was going to take your code and use it as the basis for a program that was actually a real-time little game where you could move and shoot and stuff like that. So this is that same concept where these are two separate programs, two different programs, but they both are very, very strongly tied to the realm because they include the realm.h and they use everything that's in the realm.h. They just use it differently. And so this is the beauty of it, is that whoever wrote the main.c and the test realm.c did not have to know what was in your realm.c to make it work. Well, I mean, you're writing the test realm.c as well, but you don't need to know what's inside the realm.c. You're just looking at this interface that you have and saying, okay, these are the functions that I can run. This is the object that I use with these functions. That's all I need to know. So this is what an abstract data type is. Let's just check what questions we have in there. Someone's asking you about object-oriented stuff with C. C's not technically an object-oriented language. It's not specifically an object-oriented language, but what I'm teaching right now is one of the concepts that we would consider part of a larger thing that is object-oriented programming. Object-oriented programming was a really, really big deal in, I want to say, the 90s. The 90s and the early 2000s, I think, was a really big deal. It was a way of structuring everything as objects in the same way that we have this realm as an object, and we could like ask it to do things and stuff like that. Object-oriented programs are a little bit more complicated than what we're doing now. It's got other things going on as well. But the idea of abstraction, the idea of us being able to use something without knowing what it is, super powerful. And super handy as well. So we're still teaching this, even if we're not necessarily leading you towards object-oriented programming in this course. We're leading you towards a more open-ended thinking about programming, because object-oriented programming is only one way of programming. There's many other ways of programming. Many of them are also used regularly, so we're not forcing you into one particular way here, but we're still showing you something that you can do, which is kind of handy. Mason is asking, is the same thing as including a library? Pretty much, yeah. It's very similar. What we're doing is like including a library, but we're building it ourselves. But this is more than just a library, because a library is usually just a series of functions that can be used to run something. Here we're saying something more than that. We're not just saying this is a series of functions, we're also saying here is an object. And this object is a type that we've created, and we call it an abstract type because we haven't necessarily defined how this type is built. We're just saying that we're going to use it. So imagine this, right? Realm.h. Notice that realm.h has no reference of linked lists in it. If you look through realm.h, there is no linked list. There is the idea that there's a list, but not how it's implemented. If you wanted to, I mean, you wouldn't get any marks for this, so it's pretty bad. But because what we're testing you on is linked lists. But if you wanted to, you could implement realm.c using arrays instead of linked lists. So you do the whole thing with arrays instead of linked lists, and whoever's running the main.c can't tell the difference. So that's why it's an abstract data type. If it was a type, just a type, then it has everything about how it uses memory and stuff baked in. Because it's an abstract type, we think of it as an idea. And we don't know how it's being built. All we know is that the idea of how it should work, and then we use it. So that's one of the interesting things about it. Yeah, Dean's saying the same thing. Abstraction is one of the cool things about, just using any tool that you don't know that much about. So for example, I've got this mouse here. This mouse is tracking its position on a mouse pad, and I'm pretty sure it's doing that with a camera that takes lots of photos, and it's comparing those photos against each other to figure out how far I'm moving it. I don't really know how it works. I know a bit of how it works, but I don't know 100% of how it works. I know enough to be able to use it. I don't know enough to how to rebuild it or how to make a new one or something like that. But I trust it and I use it. The H file is the same thing. You trust it and you use it, but you don't know how it was built underneath. For example, like this is in the second assignment. This is from the perspective of someone writing the main file. From the other perspective, someone writing the C file, it's like I don't know what people are going to do with this. So if I'm someone who is creating a mouse, I've got an idea about how people are going to use it, but I don't know everything about what they're going to do. I don't know every game they're going to play with it. I don't know every combination of clicks and movements they're going to use, clicks and drags and all this kind of stuff that they're going to use. I just provide the functionality and then hope that my functionality works for all the purposes. So this is where we're getting to today. Abstract data types. We can create a data type for our purpose. So this is us saying, this is the realm. The purpose of this realm is it's going to manage this sequence of locations. It's going to be able to move the enemies along those locations. And if some of those locations are towers, they're going to damage the enemies as they go past, that kind of thing. So we have that idea because we're saying, okay, this was a tower defense game, and this is the abstract data type for this game that's going to govern these things. So we can give people certain access to this object to be able to use it. I probably shouldn't call it an object because it's a type. The object you could think of as individual variables created of that type. But object is just like a word that works so well for this. But I shouldn't, because people who do real object-oriented language are going to hear me calling it an object. They go, no, it's not an object. That's a different concept. I always got to watch out because a lot of the concepts in programming have really, really simple names. So when I'm trying to describe something with a simple name, I'm slipping and I'm stepping on someone else's keywords. So it's always difficult. But our abstract data type is going to allow us to create something and say this is how you use it. But also, you cannot see the underlying implementation for how this works. You don't know how it sits in memory. You don't know whether it was made with a linked list. You don't know whether it was made with an array. You don't know who coded it and how. You don't know whether it uses a whole lot of allocated memory or it just creates everything. So without any of that information, you can't access any of the data the wrong way. So you'll note this. your main file, and you'll figure this out when you're using your test realm.c. You can't open the struct from inside the test realm.c. So you can't look inside the struct and see whether things are set up a certain way or not. And that's important. That's part of what the abstract data type is. So because you can't see what's inside the struct, you just have to ask it questions, which is what calling the functions is. It's kind of like asking it questions and saying, what do you do when I ask you to do this? And that's why we have things like when you insert something in the assignment, the function when we add a location is going to always return how many locations are in it. So that's one way we can get some information back if we can't look at the struct. And it's important, right? Because if you could look into the struct and you could get information out of the struct, or you could rewrite the struct, suddenly we're not separate anymore. Because if you can see into the struct, you've crossed the barrier, and then you're touching someone else's code and changing it. So if you rely on the fact that you can change the struct, it means that the person on the other end doing the realm.c is suddenly really fixed. They can't change the layout of the struct because someone has reached through the interface and is going in and doing things. Whereas if you only use the interface, you get up to but not through the interface. You only use the functions. Then people are free on either side to do whatever they need to do to make it work. So you can see why we have that distance between things. And this is what I'm talking about here. We hide the implementation from whoever's using it at the other end. They know how to use it, but they don't need to know how it was made, and they don't need to know the inner workings. I go back to this example I said, I think ages ago. When I'm driving a car, I don't know how an engine works. I have a vague theoretical knowledge of how an engine works, but I mean, like any mechanical engineer, it's just an undergraduate mechanical engineer would probably laugh at my knowledge of a car. I know it sets off explosions, makes pistons go up and down. Those things turn into something that makes the wheels spin. That's about as far as I can get, right? Yet I can use one of these things because someone has provided an interface for me to use this, which is an H file. The H file is like the steering wheel and the pedals, These are the functions you can call to make stuff work. You don't need to know that the accelerator changes how fast the engine is spinning based on how much fuel is going in and stuff. I don't know enough about it to really be able to say what's going on, but I can still use it. This is the same thing here. We don't know what's going on underneath the hood, but we do know how to use it because we've got the H file, and that's really simple. So this is what we're getting at with the abstract data types. Your second assignment is a huge example of this because we're not going to go super deep into that in this course. We're going to look at it, but we're not going to go super deep. So the typedef becomes interesting now because what it was before, when I first introduced it, was here's another type and a new type name, and you can just use them interchangeably. So before you were like, okay, fine, we can turn the struct pointer into this new capital letter name. Don't really know why you're doing that, Mark, but fair enough. We'll just use it because you said we're going to use it. Now you understand that if I want someone to not necessarily know that there's a struct here, I just go, this is the abstract concept of the realm. Capital R realm is the abstract concept of what it is. You will know that it's an abstract concept and you will use it as such, but you will never think of it as a pointer to a realm struct when you're using it in the main file. Because if you start to think about it as a pointer to a struct, you might start thinking that you can access the fields inside, which you can't. You're not allowed to do that. You're on the other side of the interface. The struct is on this side, you're on this side. So you can think about this abstract concept of the capital R realm, and you can pass this into functions to ask the other side to do things, but you don't get to poke into the struct when you're on that side. So when you're in the main file, you don't get to poke inside the struct. So this is your way of saying this thing is a capital R realm. This is like note the convention we have here is for the capitals. This is why we had all of your variables were lowercase, because when we were going to use our own creation of these abstract data types, we were going to use the uppercase. So this is what tells them apart. So the type that we've created is capital R realm. You don't know how it's made. You don't know exactly how it works underneath, but you can use it. So you can say, okay, I've got a realm. I know that you on the other side, who's writing the realm.c, is managing what this thing is. And I know that the only things I can ask of you are, can I use these functions that you have implemented in the realm.h? Implemented in the realm.c, but have made visible in the realm.h. So the only things you can do with the realm are use those functions to get them working. So that's why the typedef is in the header file, because the typedef in the header file means we can see this typedef, and so we can say, oh, okay, here is the type that we've been asked to use. So here is my my capital R realm, and I know that I can pass this realm into these functions. I know that it is a type now, so I can use it as if it's a type. So like it's an integer, like it's a double or a char or any of those variable types we had. But the interesting thing is we can't even kind of create one without asking for the interface to give us one. So for example, we don't necessarily have a realm in a sense where we don't just create a realm and then populate it ourselves. We create a realm by calling the function that says, hey, can you make me a realm? Because you know what bits it's made up of. So I will have a capital R realm, but I can't initialize it myself. I call a function, and then it fills it out with the information. And then after it's filled out with the information, I can then use it and things. So that's the kind of nice thing, is that you can see the type, but since you don't know how it was made, you don't pick at the inner workings of it. You only use the functions. Pretty cool, because what we end up with is a situation where we have this idea of this object. We know we can use it with those functions, but we don't actually know what it is entirely. So we get this idea where it can be much more complex than we think it is, but that's fine. We just use it for what it is. Okay, I wonder if I should go on a break now. Yeah, okay. Let's go on a break, and I'll talk about queues afterwards. So, a little thing to think about on the break, because we actually had this discussion already today, talking about different programming languages, talking about object-oriented programming and things like that. There's a lot of languages actually based on C. The ones with C in the name are highly likely to be based on C, just in case that wasn't obvious. C++ is one of the first extensions on C. C++, actually, to go back to what we were talking about, was an object-oriented add-on to C originally. Now it's like grown so much to the point where it's nearly its own language, but if you run a C++ compiler and an entire C++ environment on normal C code, it will still run. So C++ is still 100% backwards compatible to C, but it's got more stuff on top of it. So you could call yourself a C++... Don't. I was going to say you could call yourself a C++ developer, but there's a little bit more to learn before you can do that. Now, Java was also based on C. If anyone's done Java or JavaScript, you'll notice that the syntax is reasonably similar. I'm going to say reasonably similar. It's not exactly the same. C-sharp's also based on C. It's a iteration a little bit even further than C++. I have a feeling that the sharp symbol is made up of the two pluses, so overlapping each other. I think that's what that is, but I'm not sure exactly. So that's a slightly more modern variant. So there's a reason why we're teaching you C, because it's sort of this backbone that a lot of the things are based on. What I want you to think about, though, while we're learning this programming, is a lot of details that we're learning, but there's a lot of kind of ideas that we're learning as well. One of the things that's most important is what we're trying to do is learn how to communicate with computers. And we're going to end up being asked to communicate with computers with many different languages. So try to remember that the important things long term are what you want to say to the computer, not necessarily how you want to say it. Because how you want to say something to the computer is going to be the individual language. But if you can figure out what you want to do, um, and you're going to be able to bring the same approach to multiple different languages, you will find pretty quickly that you already know sort of 80% of what you need to know to be able to program in any language. Then it's a small matter then to learn the different languages and how they go about things. Um, so the idea that we're talking about object-oriented programming, people were talking about different languages and stuff like that. People are talking about different languages right now uh, in the chat and stuff. What I'm hoping that you will get towards eventually is the ability to program in any language, not just program in C. So what we're teaching you now happens to be in C, but if someone was to give you Python tomorrow and say, here's a quick idea of the syntax difference between C and Python, it'll be interesting to see how much you can do in Python, because I think that pretty much everyone who's taken this course will be able to do more programming in languages other than C than they did before this course, because I think that the way that we teach it is like more general than just working in C. Okay, let's take a break. My clock says 12 past 10 at the moment, so we'll take a quick 3-minute break. We'll come back at 10:15 and we'll launch into building an abstract data type from scratch. And we'll talk about the ideas of what I meant when I was talking about everything in the first half of the lecture when we build it. Okay, see you in a bit. All right, I'm back. I see everyone's got a lot of trepidation and a lot of issues with the second assignment. I apologize. I know there's a lot of work to do with university in general. I know there's a lot of demands on your time. I'm not sure the best way to approach this other than to say that you don't have to complete everything to have a very good amount of knowledge of what we're doing in computer science and using linked lists, and to be able to continue to then learn more about it later. So I do present a lot of ideas in COMP1511 that I don't have an expectation that you will have in their entirety and completeness by the end of the course. So it's okay if you don't know everything 100%. A lot of what I'm showing you is just this idea of what these things are, so that the next time you see them, you will get a better idea of how to use them. I think I've said this example before with pointers. Pointers and direct memory addressing and stuff like that. I know people who had, who now have reasonably long, fulfilling careers in computer science, who just simply did not get pointers in the first 10 weeks of seeing them, and honestly we only saw them 6 weeks ago, or even 5 weeks ago, so the expectation that everyone's going to understand them now is not realistic, and I don't even have it, to tell you the truth. I think that you can get by with enough of an understanding to be like, oh, I think I get what's going on here, but I'm not 100% sure. What does the star do? What does the arrow do? And all this kind of stuff, right? But I hope that I've given you enough so that you've seen it, you recognize it, you've practiced it a little, and eventually these things will all kind of click. Which is what education is. Education is not people going from 0 knowledge to 100% knowledge in something. It's people going from 0% knowledge to like 20% knowledge of something like pointers. And then the next time you see them, you'll be like, oh, let me go back and forth between what I'm doing, and I get up to like 60% knowledge. And then 10 years later or something. Well, for me, it was 15, 20 years later when I was like, teach pointers. Like really, really teach pointers. Then and only then did I reach 100% knowledge. So I think it was actually, I don't even want to claim 100% knowledge of how to use pointers. I'm sure there's stuff that I don't understand, right? So I'm at a point now where I think that everything that you're doing with pointers in COMP1511, I understand. But I'm not even going to say I'm sure of that, right? The more you say you're sure of things, the more you're going to forget that there are things that you need to learn. So please don't worry too much about trying to 100% assignment 2. That way lies madness. There's a lot of work in it. There's a lot of stuff in it that you don't need to know in order to be a proficient computer scientist. Just bear in mind, okay, with everything we're doing, that if you get a mark of 50 in this course, a lot of people think that 50 is a bad mark. 50 is the mark where I say that you've learnt enough. So think about that carefully. I say you've learnt enough, and you know what you're doing, and you can continue going if you got a mark of 50 in the assignment. Everything beyond 50 is just it's just showing off, and that's fine. Showing off is fun. I like showing off as well. And it's good to do that if you think you can. But if it's going to hurt you to push harder than you need to, then I say always do it a little, right? Always go a little further than what is absolutely necessary. I don't want people who can get higher than 50 to stop exactly at 50, because I think that's also a poor way to approach education. You want to challenge yourself, or else there's no reason to be here, But don't push yourself so hard that you end up hating what you're doing because you couldn't 100% it, because 100%ing it is kind of impossible. I mean, I've seen one student out of, how many people have I taught so far? 3,000 people or so. I've only seen one person 100% the course, and it was like it was an interesting thing. We actually had a conversation about this person between me and admin and some other lecturers in CSE to be like, wow, never seen someone ace everything in the course. So like perfect exam score, perfect all assignments and all style marks. Even those little nitty-gritty style marks no one could pick at this particular person. I'm not going to say who it is. But yeah. But you know, it's nigh and impossible to do that. So aiming at that and expecting yourself to be able to do that only leads to you not being able to meet your own expectations and ending up kind of being angry with yourself. So I think push yourself to something that you think is interesting, but try not to actually, you know, hurt yourself over it or anything like that. Okay. People are talking about that. Yep. Oh. I thought I had a cat a second ago. Oh, she's behind me. She's over there. So Chicken might be making an appearance in a second. Okay, so let's go back to my slides. And let's look at an example of an abstract data type. And I will try to move my picture so that I'm not in the way there. So let's look at a queue. I think people know what a queue is like. So remember when we were allowed outdoors? I guess when we are in Sydney, at least, there's a little bit more of us moving around. Apologize for anyone who is with us at the moment and is living in Melbourne. You probably are not spending much time outdoors at the moment. It depends also on what other countries you're in, what level of lockdown you are in COVID at the moment. But back when we could actually just hang out and stuff, we might actually stand in a queue. And a queue has a basic set of rules that we all understand, in that whatever or whoever has been in the queue the longest is the next thing to leave the queue. So you get in a queue at the back, you eventually move to the front, and then when you're at the very front of the queue, everyone else in the queue got there after you did, so you get to go next. So there's a term for the queue called FIFO, which stands for first in, first out. So it means that I just had to check in my head. It's like, does that actually make sense? Yes, it is. So whichever thing had been inserted into the queue the earliest is the first thing that will be removed from the queue. And so we could consider the queue to look something like this, where there's objects in the queue, and there's the newest object on one end, the oldest object on the other. And anytime we remove something from the queue, it would be the oldest object that gets removed. Anytime we add something to the queue, it becomes the newest object in the queue and goes on the other end. This is an abstract type. It's an abstract type because it has rules and it has ideas, but there's nothing concrete that says exactly how it works. It's just a set of ideas. And so what we're going to do today is we're going to build up a queue. We're probably not going to finish it today because we've got about half an hour left. But we're going to start looking at the queue. And we're going to say, okay, how do we do this as an abstract data type? So, move my picture out of the way. The queue is an idea where I could say do a queue with an array or do a queue with a linked list. Those are specifics. Oh, hello there. We have a friend here who's come to say hello. Hello. So when we're looking at a queue, we don't know exactly how we're going to put it together. We only know that it should definitely be organized in some way, and it should have some structure and some rules, but we don't know exactly what the implementation is. So we can have a header that says a queue should be a certain thing, it should be used in a certain way. So we should be able to add things to the queue, and we should be able to remove things from the queue. But we don't necessarily know whether it's an array or a linked list that's storing the objects. It could actually be neither of those things, but we're going to use those things because at the moment we've been studying specifically how to use either arrays or linked lists, and so we're gonna implement the queue using one or other of those. But also over this lecture and Thursday's lecture, we're going to look at how it actually doesn't particularly matter while we're using the queue what it was built with underneath. So because we've got the abstract data type, the actual implementation can change, and it's not super important. Yeah. Okay. So let's build a queue, which is an abstract data type, and know that the user or whoever's got the main file is going to see a queue. They're not going to see an array or a linked list, so they're not going to be able to change things based on it being an array or a linked list. So we're going to do a queue of integers because it's simple, which means we put numbers in, and the order that we get the numbers out should be the same as the way they went in. So they went in at a certain timing, and then they'll come out. So these are the things that we think a program that's going to use a queue might need. It might not be everything that they need, but we're gonna keep it limited for now. So we want to be able to create a queue and destroy the queue. It's the idea that we want to make something, and we want a specific function for getting rid of the queue, just so that if we're going to allocate memory for this thing, then this function is the thing that's going to free up all that memory. So we're explicitly going to say, look, you need to tell us when you don't want to use it anymore. You tell us when you don't want to use it anymore. Don't worry, we'll handle the cleaning up the memory, but you just need to let us know when. We need to add something to the queue. We need to remove something from the queue. Note that this is not add to the front of the queue, end of the queue, add to specific places in the queue. We're just saying we want something to join the queue. And when we want something to join the queue gets to tell us what the rules are. So note that because this isn't a linked list or an array, we don't get a pointer to the head. We don't get a pointer to the array, so we don't have access to it. The only thing we can do is politely request that someone gets to join the queue. And then the queue says, sure, you can add something to the queue. I will add it to the queue in the position that makes the most sense for where it should be. When we remove something from the queue, we don't say what we're removing from the queue. What we get is we just get given something. So if it's an integer, we get given an integer and say, okay, that thing has now left the queue. And say, well, where was it in the queue? And the queue says, this is the thing that you get. You don't get to know where it was in the queue. I will tell you that based on my rules in the queue, this was the thing that you should have received next. We also can count how many things are in the queue if we want to as well. So we're only going to do some of this today. We're going to start building this up because what we're thinking about is the idea of like, how do we separate this interface so that we can use it? So header file is here. I'm going to jump across to VLab. I realize now that I forgot to prepare this in advance. So what I will do is actually just download the files. So I've got my COMP1511 directory, making lecture 15. Okay. Actually, like instinct, I do it all the time where I ls into a directory that I move into, even though I've only just made it and I know that there's nothing in it. Okay, lectures. This is all the stuff that we had up until now. Week 9. Queue header, that's the one I'm looking for. Lecture 15. Okay, that should have saved that. Oops, I just opened a new terminal. Should have saved that here. Okay, so we've got queue.h. Open this in gedit. We can get this thing that I built. Well, I built this one ages ago. This is the beauty of header files. You don't really change header files because they're set up for a specific purpose and you don't need anything else. So we have this idea that I have a struct somewhere called queue_internals. I have not made it yet, so I have nothing here. I just know that there's going to be a pointer to a struct, and I'm going to use capital Q, no, Q being the same pronunciation as its first letter is going to annoy me. So I have a queue, and I can do a few things. So I have a function to create a queue, and it's going to give me back a queue. So that's good. I know that I could use that. I've got a function to free a queue where I would pass in a queue, and I don't get anything back, but I'm pretty sure this thing is going to destroy the queue. And then I can add or remove items. When I add an item, I say what queue I want to add the item to, and I say what the item's data is that's going into the queue. So I'm thinking of the queue as an abstract sequence of numbers where I put them in and they come out in the same sequence. And so the adding doesn't give me any information back. Maybe I don't need any information back, who knows. When I remove from the queue, I say which queue I'm removing from. If I had more than one, I would need to say which one it was, right? And it will give me back the integer, the next number that's in the queue. And if I want to, I could also ask how many items are in the queue there. And so what I have here is a really simple file, right? This is just one page. But this file is defining exactly what this queue can do. And if I was to look at this from a main file, I would say, okay, I can make these things, I can add and remove stuff from them. So I've got some idea of the functionality. I don't necessarily know the queue rules because the queue rules haven't been specified here. But because I know the theory of it and what's going on, I know that the queue is going to be oldest object gets removed first, newest object just goes into the queue and waits its turn. So I know that the rules are I can add anything I want, but if I remove something, it's always going to be the thing that's been there the longest. Alright, so here's the same, roughly the same file that's there. And we think about what does our header provide and not provide. Catherine's asking about whether we need to know the rules. Yeah, well, if we haven't agreed on what the rules are for a queue, it's going to be really confusing when we use it. So I could implement queue.c in a way that doesn't give me back the oldest item, and then I'd have a problem. Then we'd have to have a chat between myself and whoever's using the main file and say, okay, maybe we didn't implement this properly. In the same way that when you implement your realm.c, we have this whole specification document that says, okay, this is how we want it to behave. And we have these tests to make sure that what you're doing provides the things we expect it to. And this is exactly what happens in a software company. You'll be on either side of an interface to someone, and then when you call the function, it doesn't do what you thought it was going to do. And then you have a conversation. You go, all right, are we meeting the same specification here? So our planning that we did in advance, where we did all this work to figure out what our users needed before we built anything, all that kind of stuff, led us to the idea that we should build a certain thing. I have a feeling that we're not on the same track anymore. That won't necessarily change what's in the H file, but it might be like, look, I ran the function and it didn't do what I thought it was going to do, and then we have that conversation. So, yeah, so Catherine, as you're saying, the first in, first out rules, that's nearly like, that's the nebulous thing. That's the abstract thing that we're like, we don't even know whether that's going to happen or not. We're going to trust the person at the other end to do that. Okay, so what does a header provide and not provide? We can either take something from the front of the queue, as in like whoever's, you know, if it's a line of people. So the example that I'm using today that will be, I'm not sure how deep I'll get into this because it depends how much code we get to write before the lecture ends, is people queuing up for ice cream. So the ice cream van rolls into your neighborhood and everyone queues up for ice cream. I don't know if people even still do this. I think people who do sport and stuff like weekend sport will know that the ice cream van always turns up to weekend sport to try to sell people ice cream. But whoever gets there first gets their ice cream first. Whoever gets there next just waits in line until they can get to the front of the queue. The header does not provide us access to the internals of the queue. So I can't say, give me the third person in the queue. The queue is saying, no, you're following the rules, you can only get the first person in the queue. You don't have access to anything else. You can't even see who's in the queue in this particular implementation of the queue. Like some other building of a queue might say, okay, you can look at everything that's in the queue, but you can't remove any elements except for the most recent one. Oh, Gian said an ice cream truck did come through the street the other week and was a rare occurrence. I actually live really close to a big area of playing field, so there's netball courts, a bicycle track, and all this other stuff there. So every now and then I do actually hear the ice cream vans, so I know that they still exist. I would love if they like came to uni and stuff. I thought that would be really cool. I have a feeling we'd be more likely to get food trucks at uni, but even then, bringing stuff on campus is difficult. We tend to have our own stuff. Okay, note that we can only take one element at a time. We can only add one element at a time. We can't loop through the queue or anything like that. So the abstract data type is stopping us from ever operating the queue incorrectly. So it's stopping us from ever taking something that's not the next person in the queue. So when you think about it, if I'm the person serving the ice cream in the ice cream van and I see a friend of mine like fifth in the queue, I can be like, hey, come to the front of the queue, I'll serve you first. I can't do that with this implementation because this thing is saying to me, nah, there's only one way you can remove someone from the queue, and I am going to tell you who you get with that integer. So you can't just go serve your friend first, you've got to serve everyone in order, right? So this is this way that the abstract data type stops me from accessing things incorrectly. Okay, so let's think about what our queue.c is going to be. Matthew is complaining that you didn't get an ice cream. I didn't every time. Like I used to, when I was a kid, I used to play a lot of sport, and you go to different sports fields around the place, and if you're somewhere where there was just your team and the other team and no one else, the odds of the ice cream van were unfortunately very, very low. Yeah. Okay, so let's think about what we're going to do in our queue.c. So we can think of each function that's in the H file is being a heading. So the headings are in the header file, that's why it's called that. And so each one of those things is something that we need to implement. So we need to make sure those things work. So now we start making decisions about the actual structure underlying something like that. So we're going to start with a linked list because linked lists kind of make sense because they're pretty easy to add to one end and remove from the other in a way that an array is not as nice for doing that. We can change the length of the queue without getting any serious issues. So I think that a linked list for the moment, until I started poking at it, I think that the linked list is going to make more sense than an array for the moment for implementing a queue. Also, I just wanted to do another linked list example to show you more linked list stuff. So if we're going to do a queue.c, one of the first things we need to do is do the back end of the type definition. So let's create it. So I've got this file here completely empty for now. I'm going to start building it. Actually, I'm going to spell it out. I was going to say FIFO, but it's like, you know, I was talking about accessibility. Acronyms are just like reducing accessibility. First in, first out rules, and is implemented using a linked list. Oops. Oh, I just promoted myself to CS2511. It's not even a promotion. I'm sure whoever's teaching that would be really, really happy to not have to teach. Be like, oh, Mark's going to take that one as well. Good luck. What are we in? July? Only just still July. July 2020. Okay, so if we're going to if we're going to implement what's in this H file, we need to know what's in the H file to implement it. So one of the first things that we're going to do is include q.h. So note, the quotes says this is my file. If I was to say this in angle brackets, this would be me saying there must be a C library called q.h, and I want to include the C library called q.h. I'm pretty sure there isn't a C library implementing queues, so that wouldn't work. But if I do it in double quotes like this, this is saying the file exists and it's right there, q.h. Ooh. Let's do that again so we can see it. Oh wait, I haven't saved it yet. I was wondering why I could only see one file. Let me just save this. Okay, when I said it's right there in the folder with me. So the q.c and the q.h are right there, right next to each other, so I can do this. If they weren't in the same folder, I could do other things like /q.h and say, I know this is in the folder above. Okay, so I'm going to include this that says, I'm going to be implementing these functions, so I need to know what they are. So the first thing we're going to do is say, what is this qinternals? Because the qinternals was something that we know that we needed a pointer to, and that was the only thing that this H file and the main file that uses this is going to be able to use, is a pointer to a qinternals, but it doesn't know what the struct is and doesn't have access to it. So I know that. Did I call it qinternals? No, I'm in camel case. I don't know why this auto-completed to that, because I've not written that anywhere. Anyway, so I know that I have this struct. I don't have to have any information in this struct yet, but I know if I want to use it, I'm going to need some information. So I've said this is going to be a linked list. So if it's going to be a linked list, then I'm going to want this to have a pointer to a node. I don't have a node yet, but I'm going to call it qnode. Pointer head. So I'm saying that there's going to be a head of a list, but I do have an issue here that I'm just trying to have a pointer to a structure that doesn't exist yet. Note that I could do this. I can do this here. I've said that there is a qinternals pointer, but I have not said what a qinternals is. And I can also do this. There's a pointer to a qnode, but I have not said what the qnode is. This is a particular case of using something before it exists, because pointers are memory addresses, and I can define what a memory address is without necessarily knowing what it's pointing at yet, because memory addresses are always in a, well, if we're in a 64-bit system, they're 64-bit numbers that just address memory. So what I've said here is, like, I've got a pointer to something that doesn't exist. That's okay, because it's just a memory address for now. Later on, when we get deeper into it and we say what a qnode is, it's not just a memory address, it's also something that can access elements inside it. So long as before we use this qnode pointer, it's defined, it's okay to actually say, yeah, we've got a pointer, you'll figure out what it aims at later. So there's a slight subtlety here. Oh, Taylor's saying the reason why that's auto-completing is there's a comment here. Oh, that's bad. I should not have that in two different... So that autocomplete was a clue that I'd done something incorrect there. So if I'm going to call it a qinternals pointer, I better, even in the comment, name it the same as the variable name. So interesting. All right, so we fixed that. That's good. Okay, so we've got a qinternals pointer that points at a qnode. And so I'm going to say that if it's going to point at a structure qnode, then I'm going to have to define what this structure is. The qnode is going to be a linked list. I'm going to put some more detail in here. Implementation of a queue that stores integers. So I know that this thing has an integer. I'm just going to call it data for the thing that it's carrying. You can name that whatever you want. I could name that number or person if I'm using numbers to represent people in the queue. But if it's not specific how this queue is going to be used. Note that the idea of this being a queue for ice cream or something is not something that the queue.c cares about. The queue.c says, oh, you want to store a certain type of data? I don't care what you're using it for. I just implement the queue, you know? So it's on the other side of it. It says, I implement the functionality. You use it in whatever context you want to. In our assignment, it's more specific because the realm.h and .c are really, really specific. But I could be building a queue library here that I could use in all kinds of different programs. So I won't say specifically what it is. And because it's a linked list, it should have a pointer to the next element of the list. So basic linked list node, right? This is a basic linked list. This is the most simple. I mean, we could take out the data if we wanted to, and it would be even simpler. But this is one of the most simple linked list nodes. We're naming it queue node because we know that the queue is going to be made up of a linked list. Mason is asking if you can specify file directories. Here, you can do things by name. So I could do this. /lecture15/q.h. This will take me back to my same directory because it goes up one directory, back to the one by name that I'm in, and uses it. A lot of the time, this kind of thing happens in larger projects where we might actually have something like, I don't know if many people have looked at Linux programs, but sometimes they have a directory for includes, so they can include different parts of different libraries in it. I think in Windows projects they use a full word and things, and so you can actually do stuff like this if you want to. So if I wanted to include something from a different example, let's say just hypothetically that we kept going into another lecture series, and it's like, okay, in lecture 22 we're going to use a different header. So I could say take the header from lecture 22, and that totally works. Well, if it existed, it would work. The format of the files here works. You just got to be a little bit careful with it, because if it doesn't exist, obviously everything breaks. Oh, Charles is asking, at what point do we need to know what this is before we start using it? I think Dean's answering that. That's cool. Okay, so we have our linked list node, and we have our structure that sort of governs the linked list. This may look familiar to some of you, because the realm looks a lot like this. So we have a list of locations inside the realm, and that's a pointer to the list of locations. The locations themselves are linked list nodes, but there's this structure that sort of governs it, and that's the one that we pass around that gives access to it. So this thing's usually quite small, just a couple of pointers or other bits and pieces, bits of data, and then this is where the workhorse piece that actually joins a lot of things together. Okay, let's see where we're going in our slides. So if we want to create a queue, first thing we do is we make sure that we're matching what's in the queue.h exactly so that these things link up. So we go to our queue.h and say, okay, you want to create a queue. I'm going to copy that. And here we have a function. Note that queue.c, and this is the thing that will always catch us when we start making these, it does not have a main function, and it should not have a main function because it's always going to be included somewhere else where something else is going to use it. So the thing that's going to use it is the thing that it's going to have the main function. I just have a series of functions that implement these things so that they can be used elsewhere. So create the queue internals, and I guess make it ready for use. Just put some white space there so I'm working in the middle of the screen for you. But you know, you don't have to add a whole lot of enters at the end of your code. I'm just doing it so that when I'm lecturing, it's in the middle of the screen. That's all. Okay, so if I want to create a queue from scratch, I need to allocate the memory for things. So if I want to allocate memory, I'm going to need the standard library. up to you which order you do these things. Sometimes people will separate them with spaces as well to be like, okay, libraries are in one batch, files from ourselves are in another batch, so it's easy to read the difference. I'll keep them spaced out for now. So if I want to memory allocate, anytime I want to allocate memory, I want to know exactly how big that memory is. The thing that I definitely need is a queue internals. If I've allocated memory, I need to assign this thing to a pointer. So, two ways I can go about this. I can say struct queue internals pointer. What do we call it? New queue is equal to memory allocation here, if I want to. Or I could use my typedef, because my typedef says these things are the same. Q.C can see the typedef because the typedef is in Q.H. And so, because I'm including Q.H, I can see the typedef. So if I want to, I can make this easy on myself and not type out all of that. And I can say the queue, I've created a new queue, and I've memory allocated the queue internals there. So I've created one of these, and that's new queue. I do want to make sure that this empty queue appears as an empty queue, because for the moment the pointer to head has no value. Having no value is not the same as having null value. So me not having initialized it does not make this pointer null. It makes it some possible gibberish that could aim at memory somewhere. So I want to be careful to make sure that that is correct. So I'm going to say my new queue head is equal to null. No, I've been talking before about the fact that from here we cannot access what's inside the queue. So from the main file that looks at this queue.h, the main file cannot see what's inside the queue. Inside the C file, we have the structs. So we can see the structs inside the C file, which means we can use stuff inside. We can treat this as a pointer because we're inside the C file that knows what these things are. James is asking, is it size of struct queue internals or just size of queue internals? You are correct. It is not size of queue internals. Size of needs a type. The full type of queue internals has the keyword struct queue internals. So thank you for catching me on that. We would have figured that out when I tried to compile and it didn't work. Okay, so this should create us a new queue that says it has an empty list. I think I've done the same thing here. Oh, we needed to return it as well. Yeah. If we don't return it, this function doesn't give back its proper output. So new queue gets returned. So that's my queue create. So if I was to make a main file to make a queue, I could now make a queue. Having said that, I can't put anything in it yet, but at least I could make it. Let's look at adding items to the queue. In order to add the items to the queue, I need to figure out how I want to use this queue. And this could have gone either direction. I could have said the head is the new object and the tail is the oldest object, or I could say the head is the oldest object and the tail is the newest object. One way or the other doesn't particularly matter, so long as when I add something, it always goes on one end when I add it, and when I remove something, it always comes off the other end. So I'm jumping here. I'm skipping over queue_free because queue_free is going to be exactly the same code that we did in Battle Royale, where it's going to loop through the list and remove it. In fact, when we get to that, I may even copy-paste that code because I've written it before. So I'm going to get to the functional stuff, and so I'm going to start working on queue_add. So I'm going to copy this, paste it here. I always copy paste out of my H files into my C file because I don't want to get this wrong. I want this to be exactly the same as the declaration, because if it's not exactly the same as the declaration, so let's say I made a mistake and a typo here, they're not going to link up. So if I have this here called queue_add and I've accidentally spelled it wrong, qtadd, I will not be able to add anything to my queue because this function is different to this function. So, I mean, you know this already from doing functions. If I had queue add at the top of my list and my main and then these at the bottom, if I spelt it wrong, it would be different. Okay. So now that we're doing a linked list, we need to explain how we're doing this here. Otherwise, we could get confused with our own development of things. So in the linked list, this adds to the tail of the list. I guess that's all I need to say. Not to the tail. Sometimes when we think of head and tail, head is the first element, tail's all the rest. So I want to say to the end of the list, rather than the head of the list, to say this is going up the very far end. Okay, so if we want to add to the queue, we would add this to the very end of the list, which is here, in which case we need a way to find the end of the list. So probably we're going to loop through the list to get to the end. So I say this is the first option because I have another way that I'm going to do this. Because I've got the queue internal struct, I may not actually have to loop through every time. So I could loop through all the elements until the next pointer is null, and then I could add something to that end. Whatever the pointer was that was aiming at null, that next pointer, I aim it at the new node. But maybe I don't want to loop through the whole queue every time I add something. So let's try a different way of doing this, where we can track the final element of the linked list using a pointer. So we can use our queue internal struct, because I know I have a structure that governs the whole list. I could actually add a pointer to that, which is the tail. And I could say, have a tail pointer that points at the final object of the list, and then it's really easy for me to add something to it. So I'm going to add a pointer to a queue node that says, I'm going to point at the final element of the list. Is this looking familiar yet? Hopefully this, for everyone who's working on the assignment, this is going to look really familiar, right? Because we got a pointer to the first element of the list, pointer to the last element of the list, and now if I'm adding to the queue and I want to add something to the end of the list, I can just say add something to the tail. So if I want to, I can say, let's see, do I have a diagram for this? Yeah. I can create a new object, and then let's say connect the tail's next pointer to the new object. This is where we're different from the assignment. I'm not going to implement the assignment for you. We're different from the assignment here. But a lot of this will help you, right? Because we didn't just make up a castle defense on its own. We made up castle defense using a lot of the conventions for how linked lists are used in standard operation, right? So we're not just making up something that's completely fantastical. Although the idea of Chicken and Frankie fighting off in medieval castles is a wonderful idea, but all the implementation underneath is like standard operating. You know, this is how we often work with linked lists. Okay, so if we've got the tail, we have the new object. The null pointer hanging off the previous tail gets aimed at the new object, and then the tail pointer moves to this new object to say, okay, this is now the end of the list. So if we're going to do that, actually I've got some code here to do that. We're not going to get that much time to do it because I've only got 1 minute left, so I probably won't do the if the tail is null bit, but I'll just show you this other bit. So in order to do that, what I would do is I would say tails next aims at the new item, then move the tail to the newly added item. So what we would do first, okay, let's just say create the new item. I would potentially here do something interesting where what I would actually do is instead of creating the new item there, I could actually have QNode pointer create node. It's going to take an integer. using data as its data. I'm just going to say create a single node. I could have another function that that creates the node itself. And one of the cool things I can do with this is this keyword static. Static says that this function's not available outside this file. So this QNode pointer function that creates a node is for use in these functions only, but it's not for use in here. So if you include this, you can see you don't get create node. But create node exists only for use as a supporting function inside these. So the H file is not limiting the functions that you can write in the C file. You can still add extra functions in the C file. But if you mark them as static, then they're not available outside. So in order to use that, I would need to do the same kind of thing that we would do if we had a main file, and I would declare it up here and then use it down here. And often I might actually do something like this. To say that these things are functions that are going to be used inside this file, and they don't exist outside the file. So I make that programmatically exact by saying static. They can't be seen outside the file. And I make this clear to a person by saying, okay, these functions are going to be used only in this file to make it easier for these functions to be readable and accessible or reusable and stuff like that. Create node I think might be reused. I'm not sure. Probably not, because this is so simple. But I can start doing things like this. All right, I've gone a little bit over time here, so I should stop here. We're going to continue this on Thursday anyway. So we're going to continue this implementation on Thursday, where we're going to add things to the queue, and we're going to make a main function that uses this. So I'm going to act as both programmers in this hypothetical situation, and we'll start that on Thursday afternoon. We've got a couple of questions here. I'll answer these before I wrap up. Matthew is saying, why is this meant to seem similar to tower defense? It seems pretty different. It's because of the structure I set up here. So I've got a pointer to the head and the tail in a structure that governs the linked list, and then I have the linked list nodes themselves. So if you consider this is the realm that has a pointer to the castle and the lair, that's the head and the tail of the list. And then these are the location nodes in there. So I'm setting up a structure that is identical, but it's not the same. Obviously not exactly the same, and if you've done any work on it, you may have changed some of these things in here. But the kind of the structure of one struct aiming at either end of the linked list is the same. Okay, where are we? Other questions there. Mingji Lee is saying, is this similar to declare one current pointer and one previous pointer? Kind of, but not exactly the same. So this is saying this is a structure that is sort of more permanent. The current and previous are temporary. They're pointers that we're moving through things. But you can kind of think of it as like two different pointers aimed at parts of a linked list. So it is similar. Yuji's asking, do we, if we have created this, when we've made a new queue, do we need to make the tail null? Yes, we do. So I'll put that in now. Otherwise, it could pretend to be pointing somewhere. Oh wait, Taylor had already told Matthew why this was similar. Yeah, there you go, and you got it. Awesome. Chapper Chap's asking, do you have to state the return type for a static function? Yes. Static function, the static keyword just says this thing's not going to be available outside this file. It still needs a return type. So this thing has a QNode pointer, which should be a struct QNode pointer. I'm forgetting that there's keywords. I did mention at the beginning of the year that there would be a point we would reach in this course where the fact that I'm a native C++ speaker would mean I would make mistakes in C, and I just did that there. In C++, we would declare the queue node as a different kind of object than a struct, and we wouldn't use the struct keyword on it. And so I naturally just went there without typing the word struct in there. Matthew's asking, do we use the fact that the realm is like a queue at any point? Maybe. It's not necessarily like a queue, but it does have the same kind of directional properties that stuff moves along it and stuff, but it won't be exactly like a queue. I mean, there's a lot of stuff, hopefully. I mean, I do structure this on purpose. There's a lot of stuff in the example that I'm going to do today and Thursday with the queue that will hopefully help you understand a little bit about the second assignment. Okay, I'm going to wrap up the lecture there. People got tunes to go to and stuff like that. So I'll go to break mode for a little bit, and then I'll come back and I'll answer any questions anyone has about this code. I haven't actually ended up writing as much code as I wanted to, so maybe at Thursday at the beginning we'll do some speed coding to catch us up to where I want us to be. Okay, so I'm going to wrap up the lecture there. Stick around if you want to ask some questions. Obviously, while I'm in break mode, you can start typing your questions now, and I'll get to them when I come back. All right, back in a sec. All right, I'm back. You're welcome, everyone who is thanking. Especially thank you for thanking the tutors who drop in and answer some questions. I think we had Tom and Dean in today by the look. So they've probably both gone off to teach tutorials. I'm not sure if they both teach on the 11 a.m. Monday. Probably not. But at least one of the two of them, I think, is teaching the tutorial now that happens just after this lecture. Did anyone have any questions on the code that we were writing? I feel like I keep wanting to, I just want 15 more minutes to write some of this code here so that we could have the adding to the queue. Oh, Dean's still here, so maybe Tom's the one that's gone off to teach. Oh no, you're both still here. Someone else is teaching the first tutorial then. I can't remember who. Oh, is it? Does Kane take the first one at 11 a.m.? Or Tammy? I can't remember who. Anyway, someone else will be doing it. Okay, Weiwei's asking, sorry Mark, still confused about why abstract data type can protect the data from being accessed the wrong way. Okay, so, note, queue internals and the queue nodes are in here. They're in the queue.c, yeah? And here's the queue.h. The queue.h shows that there is a typedef to a pointer, but it does not in anywhere say what queue internals is, and note that it does not have the queue nodes at all. It says you can create a queue, you can free a queue, you can add and remove things from the queue. But if I create a main file, So I probably won't save this one because I want to build this from scratch with everyone later. But if I do this, q.h, so I've got my main and my q.h, which means that I can see stuff in here. I can call stuff like qcreate, q ice cream q is equal to so the functions in q.h that I can call qcreate is going to give me back a q, so that's the one that I want. Qcreate. Okay, so now I have a q. I have an abstract data type of a q called ice cream q. So let's say, for example, I wanted to do something silly with this q, and I wanted to add things to this q on my own. And I say ice cream q head, because I know that, because I looked in here, that it has a q node that it's head. Next is equal to, actually, head next is a node, data is equal to 10. So I wanted to go into the struct, and I say, okay, first element, second element, data is equal to 10. I try to do this because I've had a look in here and I know that these structs exist, and I know I can follow these pointers into these structs. I don't even know if, no, head next doesn't even exist, so let's just say head data. Let's make it more simple. So I say the first element, this doesn't exist either because it's null right now, but I want to make the first element 10. So I want to say that the first person in the queue is ticket number 10. So I'm just like serving people based on their numbers. You may think that this is possible because you know that this exists, but the main can't see it. So the main sees q.h here, and these are the only things it can see. These functions and this vague idea. It cannot access these because it can't see them. Because the main.c only included the h file, which is here. This is the only code that it has seen. It has not seen any of the code in here, and it cannot see any of the code that's in here, which means this is impossible. So while I've included q.h, I can't see q.c, so I don't have access to the q internals or q nodes. So this is the situation we're getting here, is that this is incorrect access to the queue. The only things I should be able to do is put a new element into the queue or take the current final element out of the queue. Those are the only things I'm allowed to do. So if I'm only allowed to do those things, I should not be able to just pick and choose parts of the queue and make changes to it. So I'm protected from doing this because I don't know what's in here. So that's how the abstract data type, by using this interface, says that the main file cannot dig into this implementation, and it can't make incorrect changes into this implementation here. All it can do is that it can say, I would like to add a new thing, or I would like to take something out of it, but I can't do anything else. So if I wanted to, I could say, look here and say qadd. Qadd is a function that takes a queue and an integer item. So I could say, take my ice cream queue and take the number 10 and add the number 10 to the queue. This line does work. it uses a function that main.c can see because it has included q.h. The q will handle exactly how to do this, right? We don't know how to do this. The q does it itself. So that's the difference here. Instead of us poking in to the linked list itself and changing things, we don't even know that there's a linked list there. So all we do is we say, okay, this abstracted data type here, this interface has said we can only use the functions provided. We can't dig beyond the functions provided and try to do our own data access and things. So this is unprotected because you can make changes to the queue that don't follow the queue's rules. So I could change something that was halfway on the queue. I mean, the queue's rules say you can't change the data once it's in. Like, you put the data in and then you don't have access to it until you pull it back out again. And you'd only pull something back out if it's gone all the way through the queue. So this says I'm following the queue rules and I'm saying please add the number 10 to the queue. The queue will decide where it goes. I don't get to decide where it goes. I can't put the number 10 in the head data. So I can't just say number 10 should be the first element of the list. I might be overriding an element if I do that. So if I already added some other things to the list and then I run something like this, if this was possible to run, it would basically damage the queue because it would be taking whoever was at the head of the queue and changing their number to 10, and we don't want to be able to do that. So this is nice and safe because it says, here's the number 10, please add it to the queue. The queue itself will have to decide where to add this, and so it will decide how it's going to follow the rules and make that work correctly, whereas this kind of explicit access to the data structure is blocked, because otherwise then the two things wouldn't be separate from each other. Did that answer the question? Hopefully that gives you a bit more information about why the queue rules are set up like that. Let me know. If you are having other problems, you can always... Oh, I forgot to say this during the lecture earlier, that there appears to be, like, people are talking about having trouble with the assignment and stuff like that. I think there's actually a lot of time in scheduled lab time at the moment where you can talk to your tutors about things. So it may be worth talking to your tutor during lab time if you need more help on how these things are working. In terms of stuff like queues, and I'm going to show you another abstract data type tomorrow, depending on how much time we have, but I will show it to you at least. There's going to be more help on these in the labs next week. Oh, hang on, we're in week 9. Oh yeah, well, at least in the tutorials, maybe in a little bit in the labs next week. All right. Hopefully I'm helping you there. Hopefully this is explaining how the abstract data type is protecting access to things. You can type stuff, let me know if you want to. I'm probably going to wrap it up there. If there are any more questions about what we're doing with abstract data types or any other questions, please type them now. And if I don't see anything in the next few seconds, I will wrap up the stream. Okay, yes, but in this example, we use the function of the interface to do what we want. Yeah, that's what we're saying. We would use the functions here. If we try to do something without the functions, that's where it's dangerous. So this is what the abstract data type does, is if this was all in one file, then the main would be able to see these, and it would be possible for someone writing this to make some mistakes and use these things. So The abstract data type means we can't do this. So because we can't access the internals, as I named them that way on purpose, the internals are something that can be accessed only by themselves, not from outside. And so because we can't do this, because this line won't work, that's us protecting ourselves from accidentally accessing the data that we shouldn't have, or changing the data that we shouldn't change. And this comes from us including only the abstract idea of what the queue is and the functions that can be used. Then what we do is we trust that the code inside the queue.c is the correct code. And we know that no matter what happens, the main.c is never able to incorrectly access the data that's there. So the main.c sees the queue as an abstract concept. Only the queue.c sees it as a concrete idea of a linked list. So the main.c can never treat it like a linked list, which means it can't do any of the weird things that might happen to be able to break the linked list. The only things it can do is it can add or remove things and stuff like that. So anytime you want to access the data from the main, you have to go via the queue and you have to say, I would like to do this, and the queue says, sure, if you would like to do that, I'm going to check that what you're doing is correct, and I'm going to make sure this works correctly and follows my rules, as opposed to trusting whatever's in the main.c to follow the rules itself. So that's the kind of difference. Hopefully there's a bit less confusion going on now there. I'm not sure, but if you're still confused, it might actually be worth going to help session and talking to someone about it, because hopefully they will explain it a different way than I do. Because if the way I'm explaining is confusing, then maybe it's good to get a different perspective on it. Also, totally fine if you're confused and want to wait until Thursday, and we'll continue building this, and then maybe you'll get more information about it then, and maybe it'll be less confusing once we dig a little further in and do a little bit more work on it. Okay, I'll wrap it up there. Thanks for coming along, everyone, and hopefully the idea of what we're doing with the multi-file projects, as well as what's happening in assignment 2, is maybe becoming a little bit clearer now. Oh, you got it now. Oh, great. I'm really happy that that's making sense now. Wait. Because I was worried that I was going to leave you with still a little bit more confusion going on. Okay, great. Thanks, everyone. I will see you on Thursday. We will continue. Obviously, this example's not finished. We'll continue this example on Thursday.